To understand invisible electrons, let's look at something we can easily see, a water system. Imagine a water tower connected to a pipe. The height of the water creates pressure, pushing it downward. In an electrical circuit, a battery does the exact same thing. It provides electrical pressure, which we call voltage. When we open the valve, water flows through the pipe. Similarly, when we close an electrical switch, electrons flow through the wire. This flow rate is what we call current. Remember, voltage is the push, and current is the actual flow. To understand electricity, we start with voltage, often described as the electrical pressure that drives the entire system. Technically, voltage is the potential difference between two specific points. Think of it as a steep hill of energy. Electrons at the negative terminal sit at the top of this hill, packed with potential energy, eager to roll down to the positive side. The steeper this hill, the higher the voltage. Mathematically, it's defined as energy per unit charge, V equals W over Q. Whether it's a small 1.5-volt AA battery or a powerful 12-volt car battery, voltage is the fundamental push that makes current flow. If voltage is the pressure, current is the actual flow, the continuous movement of electrical charge through a conductor. Mathematically, current I is the rate of flow, charge Q divided by time t, measured in amperes. To visualize this, 1 ampere means exactly 1 coulomb of charge passes a specific cross-section every single second. That's a massive 6.24 quintillion electrons rushing past this plane each second. And remember, while actual electrons flow from negative to positive, conventional current is drawn from positive to negative. As electrons flow through a circuit, their journey isn't perfectly smooth. They constantly collide with the atoms of the conductive material. This opposition to the flow of current is called resistance. Think of it as electrical friction. When electrons crash into these atoms, they lose some of their kinetic energy. This lost energy doesn't disappear. It's released into the environment as heat. While every material has some natural resistance, engineers use specific components called resistors to intentionally limit and control the current. Resistance is measured in ohms, represented by the Greek letter omega. Now that we understand voltage, current, and resistance individually, let's look at how they are mathematically locked together. This is Ohm's law. The easiest way to remember this relationship is the Ohm's law triangle. Voltage, the electrical pressure, always sits at the top. To find voltage, cover the V. The remaining variables, I and R, are next to each other, meaning they multiply. V equals I times R. If we need to calculate current, cover the I by. We're left with V over R, so current equals voltage divided by resistance. And finally, resistance is voltage divided by current. This single triangle gives you all three fundamental equations. Notice the direct proportionality. If resistance stays constant, increasing the voltage will linearly increase the current through the circuit. Now that we understand the theory behind voltage, current, and resistance, it's time to put it into practice. We are going to walk through the full process from setup to finished result, building our first functional circuit. To build this on the bench, we need 4 physical components. A breadboard for prototyping, a 9-volt battery as our power source, a standard 5mm LED, and a resistor. But before we connect a single wire, we must calculate the exact resistor value needed to prevent our LED from burning out. The first step in building our circuit is establishing the power source. We start by connecting a 9-volt battery to the breadboard. Notice the red and blue lines running horizontally. These are the power rails designed to distribute electricity across the board. By plugging in the battery clips, we flood the red positive rail, creating a reservoir of potential energy. The blue negative rail acts as our 0-volt ground. We now have a 9-volt potential difference ready to drive our circuit. Before we plug anything in, we have a problem. Our battery provides 9 volts of pressure, but our LED can only handle about 2 volts. If we connect them directly, the excess voltage will push too much current and destroy the LED. we need a resistor to absorb that extra 7 volts. To find the exact resistance needed, we use Ohm's law. First, we calculate the voltage drop across the resistor, source voltage minus LED voltage. Next, we divide that voltage drop by our target current. For a standard LED, a safe, bright operating current is 20 milliamps or 0.02 amps. 9 minus 2 is 7 volts, divided by 0.02 amps gives us 350 ohms. In practice, we'll use the closest standard engineering value, a 330 ohm resistor. Now that our power rail is ready, it's time for step 2, adding the resistor to limit the current. We calculated a need for a 330 ohm resistor. We verify this using its color bands, orange, orange, brown. Place one leg into the positive power rail and bridge the other leg into a blank component row. Unlike some components, resistors are non-polarized. This means it doesn't matter which direction you plug them in. Now it's time for the star of the show, the LED, or light-emitting diode. This acts as our circuit's load. Unlike resistors, LEDs are polarized. This means they act as a one-way street, only allowing electrical current to flow in a single direction. Look closely at the physical component. The longer leg is the anode, which must connect to the positive side. The shorter leg, often marked by a flat edge on the bulb, is the cathode. In a circuit diagram, the triangle points in the direction of conventional flow. Let's insert the anode into the resistors row and the cathode towards the negative rail. The final step is connecting a jumper wire from the LED's cathode back to the negative rail. This crucial step closes the loop. Without a continuous, unbroken path, electrons simply cannot flow. The moment the connection is made, the potential energy is released. Current flows through the resistor and into the LED. Inside the LED, electrical energy is converted into photons. We have successfully built a complete working circuit. Notice the continuous flow of electrons. This unbroken cycle is the fundamental basis of all electronics. Now that we've built a working circuit, let's look at the 3 most common mistakes. Mistake number 1, the short circuit. A short circuit happens when a wire accidentally creates a direct path from the positive to the negative terminal, completely bypassing the resistor and the LED. Remember Ohm's law. Current equals voltage divided by resistance. If resistance drops to practically 0, the current spikes to dangerously high levels. This massive rush of electrons generates extreme heat, which can instantly melt your wires, damage your breadboard, or even cause the battery to explode. The second most common mistake is connecting an LED directly to a power source, completely forgetting the resistor. When you close this circuit, the 9 volts from the battery push electrons through the LED with extreme force. Without a resistor to limit the flow, the current spikes dramatically. The LED flashes brilliantly for a fraction of a second, and then it burns out. Mathematically, Ohm's law explains this perfectly. If resistance is nearly 0, the current approaches infinity, instantly destroying the component. You've double-checked your math, placed the resistor, and connected the battery, but when you power it up, nothing happens. Welcome to mistake number 3, reverse polarity. Unlike resistors, LEDs are polarized, meaning they only allow current to flow in one direction. In a schematic, the diode symbol looks like an arrow hitting a wall. If inserted backwards, that wall literally blocks the electrons, breaking the circuit. Fortunately, the fix is easy. If your math is right but the LED is dark, simply flip it around so the long leg faces the positive terminal. Calculations are essential, but real-world engineering requires verification. Enter the multimeter. To measure voltage, we place our probes across the component in parallel. Touching the battery rails confirms our 9-volt source. Measuring current is entirely different. You must physically break the circuit to force the electrons to flow through the meter. By placing the meter in series, we verify our circuit is drawing exactly 20 milliamps, just as we calculated. Remember the golden rule. Voltage is measured across, current is measured through. This prevents blown fuses.